grade 9, and into new material where we look at later on the connection between electricity and magnetism. Today's just a focus on magnets, and there's some great labs. Hope you get to doing them. Okay, so first of all, magnetic force is a type of force, and you've seen it and experienced every time you put a magnet on your fridge, right? So the definition is the force experienced by a ferromagnetic material. So ferromagnetic just means something that can become a magnet. A paperclip can become a magnet, so it's ferromagnetic when in a magnetic field, and that's just the space near a magnet. So if you have a strong magnet and you put a paperclip somewhere close to it, that paperclip will probably feel a force and move into your magnet. That's all. That's magnetic force. Yeah, so ferromagnetic can become a magnet. If it's a strong ferromagnetic material, it'll actually stay a magnet. And usually iron will do that. They become magnets. Okay, but weak ones like paper clips, right? It'll become a magnet for a short time, but then you can make it join up with other things and they'll stick together. But over time, that just dissipates, and so that's a weak ferromagnetic material. The reason that some materials become magnets is because we say domains is the science word, but the particles inside will all line up in the same direction. So if they're not a magnet, they'll be all over, but if they become a magnet, they'll all line up together, and that's why you have two poles on a magnet. You have the south pole and the north pole. Yeah, similar to electromagnetism, the law of electricity, the law of magnetic poles, where in electricity, negative attracts positive, or opposites attract, and similars repel. Exact same with magnets. North attracts south, north repels north. This is something, hopefully, again, you get to the lab and do this yourself, but you can, of course, you've seen this before, maybe you're not, but if not, just do it. But if you had, iron filings and you drop them all around a magnet, you should get something that looks like this, and this is a picture of a magnetic field. And it just means that, this is the area around a magnet, and if you put something in this area, it will feel a force. And the direction of the force will be in line with the lines here. So right here, the force will be either like just in that direction exactly, right? The motion of it will follow the path of these little filings. So magnetic field lines are the lines themselves. You should notice that, as you create a magnetic field, they never cross. Part of what, and they're denser where the field strength is. So the field strength is strongest sort of near here. See how weak the field strength is right here, by the way? Something to think about with my bonus question. Indicate the direction of a compass would point if in that location. So this part's the part that's made up, right? By convention, we say that, like, there's obviously no arrows on these, but if you were to draw them, you would draw them with arrows pointing south, to the south magnetic pole. So just some examples, and again, it'd be great if you did this lab. You could do this yourself, right? So you see an attraction of magnets, opposite poles. These are two similar poles. That's a north and that's a north. So these are repelling, and that's what it looks like. Whereas if this was a north and this was the south, that's what it would look like. That's how we draw them, though. Okay. So we draw them to show that same picture that we saw a few in this case here, right? We're trying to draw this picture, and what we add to it that's different is we add arrows pointing south. Okay. Earth, of course, has a magnetic field. One weird thing that might throw you off is the fact that what we call the North Pole is actually the South Magnetic Pole. And you might think, well, that's really dumb. Why would you do that? Why not just call it the South Pole then? But the reality is that Earth, there are something called geomagnetic reversals where, and not going to happen in our lifetime, but every couple million years or so, the magnetic field switches. It actually reverses. So, yeah, the North Geographic is actually the south, and it's actually at a bit of an angle. So from our point of view, we hold a compass. It's going to point north, what we think of as north. But if you were right here, for example, see where my little mouse is, your compass wouldn't point to the North Pole anymore. It would point off in this direction. because the actual north magnetic field, like the magnetic field, is not exactly on the same as what we call the geographic axis for North to South Pole. Here's an example. Oh, this is the pole reversal, right? So obviously this is what it looks like now. And then it's scrambly during, and there's theories that maybe some extinctions have happened during geomagnetic reversals that might explain the extinction of the dinosaurs, because when it happens, we're actually protected by Earth's magnetic field from all the charged particles coming from the sun. And there's a theory. I don't think it's that strongly held, but a theory that when there was a geomagnetic reversal, this field wasn't enough to protect the Earth from all the charged particles from the sun, and that caused an extinction. Which, like I say, it's a theory. I don't think many people believe it, but okay. Then of course there's the wonderful northern lights, and they're caused by we call them the aurora borealis, but they're caused by the Earth's magnetic field. And let's just watch a little video. Another little video.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts. On the Sun, a star of average size among billions of other stars in our Milky Way. The Sun acts as an enormous power plant. The energy is created deep inside the core of the Sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the Sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the Sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the Sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. After 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
That's, by the way, how cool physics is. Okay, that's done. So, yeah, that's the Aurora Borealis. That's just a brief outline of magnets in general, and yeah, now hopefully you go and do that lab because it's fun and cool. And yeah, that's it for now. Tomorrow we'll talk about the connection between magnetism and electricity. That was my dog, by the way, if you heard that.